Hello everyone, this is Phys103. This is on atomic structure and we are continuing currently for the many electron atom system. And in this lesson, we are going to discuss the Pauli exclusion principle. Okay, so to understand the structure of many electron atoms, we have come up with, first, if you watch the previous video, we have talked about the central field approximation. So the central field approximation, simply put, you are treating all the other electrons outside the nucleus, and you are leaving just one electron to be outside the nucleus. So you have your protons here and neutrons, and the other electrons outside the nucleus is treated just like a shell that cancels out or changes the charge of the nucleus. So to see how this model fails, this one electron quote unquote one electron system, we would expect it to be always in ground state. So why would we expect it to be always in ground state? Because that's the nature of everything in the universe. We want to always move to the lowest possible energy state. You wouldn't see for example, a ball that moves up. It wants to move always in the lowest possible energy state. So we would expect this electron to be always in the ground state. Okay, so what if we add in another electrons, or we put in more electron, we transition to a higher element in our periodic table. So all electrons that we add into this central field approximation model will have all their electrons in the ground state. So they will be always in the ground state. So when something is in the ground state, we may say that it is stable. So it is stable. But upon adding more electrons, we don't observe stability in atoms. So for example, we have elements fluorine and I think fluorine is Fl, fluorine, neon, and sodium. Okay, so these elements have atomic number Z equals 9 for fluorine, Z equals 10 for neon, and Z equals 11 for sodium. So all of these have, for example, fluorine to neon, you just add in on one electron. Neon to sodium, you just add in one electron. But these three elements have very vast differences. For example, fluorine is a halogen. Neon is a noble gas. Sodium is an alkali metal. So all of these are due to just the addition of one electron. But in our central field approximation, if we add in electrons to our system, we would expect that they would all be at the ground state, they would all be stable. But yet, we observe that they have very different properties. So in order to solve this puzzle, there comes the physicist named Wolfgang Pauli. So Wolfgang Pauli, he brief history introduction. He is a Austrian, of course, he's a physicist, Austrian guy. He invented the exclusion principle. So this is Pauli's exclusion principle. So let's state it formally. No two electrons can occupy the same quantum mechanical state. In a given system. Okay, so no two electrons can occupy the same quantum mechanical state in a given system. So for every electron, its quantum mechanical state, defined by the 4 quantum numbers, must be unique. So no two electrons can have the same values of all 4 quantum numbers. So other words to say this is that each electron must correspond to a certain distribution of probability cloud in space. So we have talked about how different quantum states give rise to different shapes. So that is the behavior of each electron. So imagine, for example, an electron in the ground state, it will be very different on the electron in the higher states. It will be very different for the electron in any other state. So this solves the puzzle on the central field approximation. So no longer is the electron there's our neutrons. No longer is the electrons or the single electron confined to the ground state. Not all electrons can be confined to the ground state. So, Pauli's exclusion principle gives rise to everything in the periodic table. Every trend you see in the periodic table is actually explained by Pauli's exclusion principle. And this is a very quite complex mathematical task. This is solved in a formal quantum mechanics class. But it is important to take note that this exclusion principle is different from the electric repulsion between electrons. So Pauli's let me write Pauli's exclusion principle is not because of electric repulsion. So you might be wondering, how come no two electrons, for example, I have one electron here and then one electron here, how come they cannot share the same state? So this is not because of electric repulsion. Sorry. This should be here. No, this is not because of electric repulsion. This is a fundamental fact of quantum mechanics.